Okay, before we start, a small announcement. Tomorrow is Dies Academicus, in case you didn't know, and that means there are no lectures tomorrow, therefore also no exercise courses. And so this means there's no exercise course tomorrow. And the exercise sheet, on the exercise sheet is written that you should return it by tomorrow in the exercise course. But since there is no exercise course tomorrow, you can return it until Friday in the lecture. So tomorrow there's Dies and therefore no lectures and exercises. And the exercise sheet can be returned on Friday in the lecture. And therefore also the new exercise sheet will not be handed out tomorrow, but also on Friday. Okay, so what did we do in the last lecture? We tried to define the semantics of functions that are defined by algorithms that use recursion. How did we do that? Now there were two possibilities. Let's look at this example. Here we have, in the first two lines, the definition of the factorial function in Haskell. So how is it defined? Fact is a function from integers to integers, and it is defined like this. It's a function, so it takes an integer x, and then this is the result. If x is less or equal than 0, the result is 1. And otherwise, fact calls itself recursively with x minus 1, and the result is multiplied by x. Now the problem is that fact is defined by recursion. If it were not defined by recursion, then the semantics would be easy. What we would do is we would simply first determine the semantics of this right-hand side. And if we know the semantics of this right-hand side, then the meaning of this function declaration is that fact will be assigned the same semantics as the term on the right-hand side. Now for functions that do not use recursion, we can proceed like this. But since fact uses recursion, one idea to avoid this is we replace fact by a sequence of non-recursive definitions. So we define new non-recursive functions, fact0, fact1, fact2, and so on, defined by recursion. So fact is a function which takes an integer and returns bot. Bot is another function which we... können Sie ein bisschen stiller sein? So fact0 is defined as follows. It takes a number and it returns bot. And bot is a predefined function. Well, it's a function that we predefine, and it should always be undefined. Fact1 looks like the factorial function, but the difference is that the recursive call is replaced by a call to fact0. So when we define fact1, we use the previous approximation. So in other words, fact1 is like the fact function, but only for those inputs which take at most one recursive call. So with fact1, you can do one recursive call, and if you need more than one recursive call, then fact1 is undefined. And with fact2, it's the same as fact, but in the recursive call, instead of the recursive call, we have fact1. So this is like fact, but you can use at most two recursive calls, and if you would need 3 or 4 or more, then you would be undefined. Now, how can you generate these approximations systematically? You can do this as follows. You can define a function ff. Ff takes one approximation and gives you the next approximation. So if you apply ff to approximation number I, you get approximation number I plus 1. And this function you can immediately get from the definition of fact, and it looks just like fact. The only difference is that the recursive call is replaced by a function variable. So if you apply ff to fact1, then on the right-hand side you have this stuff, but here you have fact1. So this is the right-hand side of fact2. So in other words, ff of fact1 is fact2. So in this way, you can produce these approximations. Fact0 is the bottom function. Fact1 is ff applied to fact0. Fact2 is ff applied to the bottom function, and so on. So if this is red, you cannot see this on the slide, but believe me, this is red. So the red functions, they should be the semantics of the black functions. So if this is the semantics of this Haskell function ff, then what you can do is you can apply ff 0 times to the bottom function, 1 time to the bottom function, 2 times to the bottom function, and so on. And in this way, you get the semantics of fact 0, fact 1, fact 2, and so on. So you get fact, this is the semantics of the Haskell function fact 0. This is again red. So the red function fact 0 is the semantics of the Haskell function fact 0. So if you take fact 0, fact 1, fact 2, and so on, we have a chain. It's a chain of functions because they get more and more defined, and we take the least upper bound of this chain. This is supposed to be the semantics of this original Haskell function fact. So this is one way of defining the semantics, generate these approximations, and then take the limits of these approximations, the least upper bound. And this is the semantics of fact. Now that's one way of defining it. And the other way of defining it is the following. Instead of building this chain and taking the least upper bound, we instead take the least fixed point of this function ff. So this means here we take this function ff, and if you recall how ff looks like, ff is just like the definition of fact. The only difference is that the recursive call is replaced by a function variable. And a fixed point of ff means this is a function that satisfies the defining equation of fact. And there may be many functions that satisfy this. We want to take the smallest one, the least fixed point. And this means it should be as undefined as possible. It should only be defined if the semantics, if the definition of fact really enforces it to be defined. And these two semantics give us the same result. So it doesn't matter if you define it as the least upper bound of this chain or if you define it as the least fixed point of this ff function. And that this really gives the same result is the so-called fixed point theorem. So what the fixed point theorem tells us states that we can really define the semantics of recursively defined functions like fact as the least fixed point of the corresponding higher order function. Higher order function ff. So this least fixed point really exists. So the theorem says that the least fixed point exists, and moreover, the theorem also tells us how it looks like. Namely, we can compute this least fixed point by building this chain and then taking the least upper bound of this chain. And the theorem says how the least fixed point looks like. And in fact, this theorem which says there is a least fixed point and you can get it by building this chain, this theorem holds for any continuous function. So now we can see why we restricted ourselves to continuous functions, because only for continuous functions we can be sure that there is a least fixed point. So this only holds for continuous functions. So this is the reason, the main reason for the restriction to continuous functions. Okay, so here is the theorem. And this is one of the central theorems of the lecture. So this is theorem 2117, the fixed point theorem. And this theorem ensures that we can really define the semantics in the way that we do it. And this is by Kleene and Tarski both formulated variants of this, and this is pretty old, so around 1952. So what it says is, if we need a complete partial order and we need a continuous function, and then this continuous function has a least fixed point. So let this here be a complete partial order on some set D, and let f go from D to D and be continuous. So when we use it for semantics, then this f is this higher order function ff. This higher order function which computes approximations, for example, to the factorial function. And we want to find out what is the least fixed point of this higher order function, because this least fixed point we will use as the semantics of fact. And then the theorem says, then f has a least fixed point. And moreover, we know how it looks like. The least fixed point of f is the least upper bound of this chain, of the chain f applied to bottom 0 times, 1 times, 2 times, and so on. Now maybe I put on this other slide again so that we can see ff. Okay, when we use it for the semantics, we look at this function ff, and we apply ff to the bottom function 0 times, 1 times, and so on. And the theorem says the least upper bound of this chain, this function here, is the least fixed point of ff. In other words, this is a function that satisfies the defining equation of ff. So if we apply ff to the function, we get the function itself. In other words, if we take the right-hand side of the factorial definition, but replace g by this least fixed point, then we get this least fixed point again. But this theorem holds for any function. So this does not only hold for ff. It simply says all continuous functions have a least fixed point, and you get it in this way. Okay, we will prove this theorem. Now, we first have to show that the least fixed point exists. So what we will do is we will show that this least upper bound exists, and then we show that this least upper bound is indeed the least fixed point. So we proceed in 3 steps. So step 1 is show that the least upper bound of this set here that this exists. Now, when we want to show that this exists, how can we do this? We know that this is a complete partial order. Complete partial order in particular means every chain has a least upper bound. So if we know that this here is a chain, then we know it has a least upper bound. In other words, then this least upper bound exists. So since this order here is complete, it suffices to show that this set here is a chain, because for a complete order, every chain has a least upper bound. That this set here is a chain. Okay, so what does it mean to be a chain? A chain means we can order the elements. So we can put these elements into some order such that one element is less defined or equal than the next, and this is less defined or equal than the next, and so on. And what we show is, we show that fi, if we apply fi times to bottom, then the result is less defined or equal than if we apply fi plus 1 times to bottom. And if we can prove this, then obviously bottom is less defined or equal than f of bottom, and this is less defined or equal than f applied to bottom twice, and so on. So then this is clearly a chain. Okay, so it's sufficient to show this statement star. Now how can we show this? We simply use induction on I. So we prove star by induction on I. So the induction base case is the case where I is 0. Now if I is 0, then we have to prove if we apply f 0 times to bottom, then the result is less defined or equal than if we apply f 1 times to bottom. So we have to show if we apply f 0 times to bottom, that means we just take bottom. So bottom must be less defined or equal than f of bottom. Okay, now this is clearly true because bottom is the smallest element. So bottom is less defined or equal than anything. So this is trivially true. Now the induction step. As induction hypothesis, we assume that the statement holds for I. So f of I, fi times applied to bottom is less defined or equal than fi plus 1 times applied to bottom. And what we have to show is the induction conclusion. If we apply fi plus 1 times to bottom, then this is less defined or equal than f applied I plus 2 times to bottom. So we know this, and we want to show that. Now, why does this imply that? Now, we know something about f. F is not completely arbitrary. F is continuous. And continuous is... And therefore it's monotonic. And monotonicity implies exactly this, right? So if it's monotonic, then this means if we have two arguments, this one is smaller than that one, and we apply f to both these elements, so if we apply f here and there, then again, the result here is less defined or equal than that. Yeah, and if we apply f here, we get fi plus 1, and if we apply f here, then we get fi plus 2. So this immediately follows by monotonicity. So this follows by monotonicity of f, because indeed continuous implies monotonic, and this was the theorem we had before. This was theorem 2115a. 2115a. Okay, so this means we have proved this statement 1. This is really a chain, and therefore there is a least upper bound. Now, the next thing we show, as I said, we proceed in 3 steps. We now know that this thing here exists. So this here is a chain, therefore it has a least upper bound. Now we have to show that this is indeed the least fixed point. So there are two things that we have to show. We have to show that it is a fixed point, and then afterwards we show that it is even the smallest fixed point. So step 2 is show that this least upper bound here is a fixed point of f. So at that point, we just show that it is some fixed point, not necessarily the smallest one. That it is the smallest one we will show in step 3. Now, what does it mean to be a fixed point? A fixed point means x is a fixed point of f if f of x equals x. So what we have to show is, if this is a fixed point, then this means if we apply f to this thing here, then we get this argument again. So this is what it means to be a fixed point. Okay, let's try to show it. So we want to apply f to the least upper bound of this chain here. We know now that it is a chain. Now, how does this look like? Now again, we have to take into account that we know something about f. F is continuous. Now, continuous means if you apply f to the upper bound of some chain, then you can exchange building the least upper bound and applying f. So instead, you could first apply f to every element of the chain and build the least upper bound afterwards. This is the definition of continuous. So we can now apply this definition. Since f is continuous, we know that instead of taking this chain and first building the least upper bound and then applying f, we could also do it the other way around. So since f is continuous, we could first apply f to every element here. So we apply f to every element in here. And then we build the least upper bound, since f is continuous. Now, clearly we have to use this somewhere, otherwise I would not have introduced continuous. So what does this mean? This means we apply f to every element of this set. So let's do it. So if the element of the set is f applied I times to bottom, and we apply another f to it, then what we get is f applied I plus 1 times to bottom. Okay? Now what do we want? We want that the result of this thing in the end is the original argument again. So we want this in the end. Now how does this differ from that? Now it's almost the same, but there's one slight difference. How does this set behind this lub, so the set where f is applied I times to bottom for all I, how does this differ from this set where it's applied I plus 1 times to bottom? Sorry? It starts by 1. So the smallest element of this chain is not bottom, but f of bottom. So this is bottom, f of bottom, f bottom, and so on. And this is f bottom, f bottom, and so on. So this here, one element is lacking. The bottom element is lacking. But what we do in the end is we build the least upper bound. So there are many, many big elements in there, f bottom, and so on. And if we add one more element, which is smaller than anything else, this will not influence the least upper bound. I mean, the least upper bound is bigger than f of bottom, f bottom, and so on. So if we put in one more very, very small element, that makes no difference. So we can simply say, well, instead of just taking these elements, we can also put bottom, also add bottom. This will not modify anything. So the least upper bound is not modified if we add bottom, since bottom is the smallest element. Okay, and as we just noticed, this thing is the same as writing f applied I times to bottom for all I, which is what we wanted to show. Okay. So now we come to step 3. We have shown that this thing here exists and it is a fixed point of f. Now we have to show that it is the smallest fixed point. So this is the last step. Show that this here, I element n, is really the least fixed point. So how will we do this? We know already it is a fixed point, but we have to show that it is smaller than any other fixed point. So let's take another fixed point. Let D be another fixed point. Of f. What we want to show is that our fixed point is smaller. So what we have to show is that our fixed point is less defined or equal than D. Now, how can we do this? What we will do is we will show that D is an upper bound to this set. So D is bigger than every element in this set. Then D is also an upper bound, and therefore the least upper bound of the set must be smaller than D. So it suffices to show every element of the set here is less defined or equal than D for all I. So let me call this double star. Now, why is this sufficient? If this is true, then D is an upper bound. D is bigger than every element in the set. But if D is an upper bound of the set, then the least upper bound must be smaller than any other upper bound. So it also must be smaller than D. So the reason why this is sufficient reason, then D is an upper bound, and therefore the least upper bound is smaller, is less defined or equal than D. Okay, and how do we show this? Well, if we have to show something like this, something holds for all natural numbers I, then the straightforward way to do it is induction. So we prove double star by induction. Okay, so again, what is the induction based? So this is the case where I is 0. What we have to show, therefore, is if we apply f 0 times to bottom, then we get bottom. Bottom is less than or equal to D, and D is some other fixed point of f. Now, this is trivially true because bottom is the smallest element. And in the induction step case, now our induction hypothesis is that if we apply f I times to bottom, then this is smaller than D. And what we want to show is that this also holds if we do it I plus 1 times. Now, why does this imply that? It's monotonic. So by monotonicity, f is monotonic. By monotonicity, this means if this holds, then it still holds if we apply f to both sides. So by monotonicity, the induction hypothesis implies if this is true, it's also true if we apply an f on both sides. And now this here means we apply fi plus 1 times to bottom. And now here we have f of d. What we want is d. How do we get from f of d to d? Right. So if d is a fixed point of f, fixed point means if you apply f to this argument, you get this argument again. So this is d, since d is a fixed point of f. Okay, and that's the end of the proof. Okay, so basically what does the fixed point theorem help us? So by the fixed point theorem, by this theorem we know that if we have functions like ff, and this ff we get from expressions from our programming language. So functions like ff, which are obtained from expressions of our programming language, so such functions are always continuous. And if we know that, so then this theorem says us they have a least fixed point and we know how to get it. Hence, they have a least fixed point which can be obtained as the least upper bound of bottom, ff bottom, and so on. And this means if we have a recursively defined function like fact, then we can understand this definition like a kind of equation which is a constraint for the semantics of fact. So this equation means the semantics of fact must be a function such that this function is, if we replace fact by this actual function, it should be the same as the right-hand side when we replace fact by this actual function. So this function has to satisfy this equation. So these equations are kind of constraints, and these constraints say how the semantics of this function looks like. And the fixed point theorems guarantees us that these constraints have a solution. So these equations have a solution. So for the semantics, we regard the Haskell function definition as an equational constraint. And the fixed point theorem guarantees us that this equation has a solution, and it even has a smallest solution. So such an equation may have many solutions, but for the semantics we take the smallest one. So the fixed point theorem guarantees that this equation, or this equational constraint, has a smallest solution. And so we can define the semantics of fact to be the smallest solution of this equation, because we know that it exists. So therefore, we can define the semantics as this smallest solution. So the fixed point theorem is the main justification why we can define denotational semantics in this way, why we can say the semantics of a recursively defined function is the least fixed point of the corresponding higher order function. It's the least function which satisfies the defining equation of fact. Okay, so now we can, after all this justification and motivation, we can now formally define the denotational semantics of Haskell. So, section 2.1, where all the mathematical backgrounds needed and all notions. Now, section 2.2, we really define the denotational semantics of Haskell, where we, of course, use all the notations and result from section 2.1. And we will proceed as follows. We will, in 2.2.1, we will first again define the domain. I mean, we have defined the domains for base types, we have defined the domains, or given an idea for domains for tuples and for function types. But we have not yet regarded polymorphism, and we have not yet regarded user-defined types. So here we define the domain that we use, also for those things that we excluded up to now. So also for user-defined data structures, and for polymorphic types. Now, up to now, we only looked at monomorphic types, and we did not look at user-defined data structures. We only had base types like int, bool, float, and we discussed what happens if we build tuples of types and what happens if we build functions. But these two things we did not look at. Now we have to look at that as well. And then here we define really this function val. So this is the domain dom, which we will use. And then here we define this function, which really gives us the semantics. So it's a function which takes a Haskell expression. So this is an expression of Haskell. And every Haskell expression is mapped to an element of DOM. So here we define the semantics formally. But to make life easy, we only define this for a small subset of Haskell. So for something that I call simple Haskell. So simple Haskell is a subset of Haskell which in particular excludes pattern matching. So this is a subset of Haskell which in particular has no pattern matching. So the things in simple Haskell, they look like this factorial function up there. So they have just one variable on the left-hand side, and then there's an equation and some stuff on the right-hand side. So this was the reason for writing the definition of fact in the way it is written up there. And now, of course, this is a rather heavy restriction, because if we don't have pattern matching, then this is a really small subset of Haskell. And therefore, in section 223, we present a transformation to transform a more or less arbitrary Haskell program into a program in simple Haskell. So this is a transformation from full Haskell to simple Haskell. And so we can then define the semantics of arbitrary Haskell programs by saying, well, if we have a Haskell program, we define the semantics of this full Haskell program to be the same as the semantics of the corresponding simple Haskell program. So this extends, this says, well, for every full Haskell program, there's a corresponding simple Haskell program, so you don't need pattern matching. You can also define your program without pattern matching. This transformation works automatically, so even a machine can do this. And then for simple Haskell expressions, we really define this function. So we say, for a simple Haskell program, we can say what its semantics is. And for a complicated Haskell program, you have to take the corresponding simple Haskell program, which is given to you by this transformation. So this is the plan, how we will define the semantics. So let's start with this domain. So section 221 is the construction of domains. Now, what we will do is we will now extend this idea of having, we had domains for every type. So we had said how the domains for base types look like, and we gave an idea how it looks like for tuples and for functions, but we want to do this for user-defined functions as well. And to do this, we need two operations on domains. So if we have one domain, then we need an operation which gives us a new domain from this domain that we already have. And we need two operations to create new domains from domains that we already have. And these two operations are called lift, and it's called coalesced sum. Verschmolzene Summe in German. So coalesced means verschmolzen. Okay, let's define the lift. The lift is something very simple. The coalesced sum is also not very complicated, but the lift is even easier. And we need these two operations to get a new domain from a domain that we already have. So what does lift mean? Now assume we have already some domain or some set. Let D be a set with a relation less defined or equal. And then the lift of this set is simply the operation where we add one more element to D, namely an element which is smaller than everything we had before. So we add a new bottom element to D, which is smaller than everything that we had in D. So the lift of D is denoted D bottom, and it consists of basically D and another element. But in order to distinguish the elements in D and the elements in D bottom, we mark those elements which come from D by a small, by little d here, which indicates this is an element which comes from the original set D. And we add another new element bottom. So this is a new element D, a new element bottom of D bottom. So this basically is a marked version of the elements from D. Now, how do we define? We have a less defined or equal relation on D, and we also want a less defined or equal relation on D bottom. And how will this be defined? The relation less defined or equal on D bottom is defined as, well, an element E is less defined or equal in D bottom than E prime if, and only if, well, either this is the new bottom element, so this is the new bottom element, or they both come from D. So this is an element D from the old set capital D. E prime is also an element D prime from the old set capital D. And in this old set, D was smaller or equal than D prime. So this is this relation from D. And we call this also a domain. So if D is a domain, then D bottom is also a domain. And now, instead of writing these marked versions, we sometimes also write D in D bottom instead of this marked version, instead of D marked with D. So this means a marked version of small d which is in the set D bottom. So this means a marked version of D which is in the set D bottom. So the idea of the lift is add one new element to the set which is smaller than everything you had before. Now if you want to depict this graphically, you can do this like this. You can say, well, this is my set D. Here is the smallest element of D, and there are bigger elements. So here at this point, you probably have bottom of D. If D has some bottom element, if it has no bottom element, then you have nothing. And now, by the lift, what you do is you add one more element here, which is this new bottom element. So, examples. Well, as examples, those domains that we have for the base types, they were generated in this way. So, the domain for expressions of type int is exactly this. We took the set of integers and then we applied the lift. And by the lift we added one more element bottom. And we indicated this by writing bottom as an index to the integers. And this operation of writing bottom to some set is called the lift. So we have used this already, but you can define this for any set. We did it for the integers, we did it for the booleans. Here we took the set true and false, but lifted it. And so then we have true, false, and bottom. And this bottom is smaller than everything we had before. So all the domains for base types were built in this way. Okay, so we now know, well, we knew this already before, but we now recapitulated how domains for base types are built. They are built by taking the set that you would expect, like the integers or the booleans or the floating point numbers, and then taking the lift. So the lift adds one more element, which stands for undefined. Now let's recapitulate how we built the domain for tuples. So how do we build the domain for tuple types? Now, up to now, we said, well, suppose we have something like int. So if the type is int, then what is the corresponding domain? Now, what we have said up to now is, well, we take the domain for this type and the domain for this type, and we build the cross product. So we take the domain for int, which is that bottom, and we take the domain for int again, and then we take this. And now that's not a good idea. So this is not the domain that we take, because up to now we, well, intuitively said that this is the domain for tuple types, and this is almost true, but not completely true. The domain should not be this, and why should it not be like this? So I will modify this. Let's look at an example. So let me define two constants in Haskell, both of type int, int. So I define C in the following way: C equals C. Now this is of course a rather nasty definition, this will not terminate. And I define D, also of type int, int, as follows. Let bot equal bot. Now bot is of type int in the tuple bot, bot. Now, if you want to evaluate C, this will not terminate. If you want to evaluate D, this will not terminate either, because what you will do is the result of D is a tuple of two elements. If you want to evaluate the first component, you run into non-termination. If you want to evaluate the second component, you run into non-termination again. Nevertheless, C and D should not get the same semantics. Because if you define another function, I will define another function f, and f operates differently on C than on D. So, I mean, they both look pretty undefined, but C is less defined than D. So D is defined a bit more than C. Let's see why this is the case. So let's think about what the semantics should be here, and let's think about what the semantics should be there. And we will see that the semantics should not be the same, because there are functions that operate differently on C than on D. And here's an example. So f is a function which takes such a tuple and returns an integer, say. And now what f does is it takes a tuple of the form x, y, and it returns 0. And now this is not the same as the function g. Let me write down another function g. Same type as f. And g of z equals 0. Now we can also think about the semantics here and about the semantics here. So this x here has type int, and this y has type int as well. But this z here has type int, int. Now, okay, all this stuff you can define in Haskell. Now, what happens if you want to evaluate f of C? What happens if you want to evaluate f of D? What happens if you want to evaluate g of C? And what happens if you want to evaluate g of D? So, any suggestions? Let's start with G. G is the easier case. So G of C. If you call G of C, what will happen? You will try outermost evaluation. G of C. Here you see the pattern matches. I mean, Z matches is a variable, it matches everything. So it matches also Z, it also matches C. So G of C evaluates to 0 immediately. So this will terminate and give us 0. Now G of D, same thing. G you can apply to anything of the right type. It matches, so the result is 0 as well. So for G it makes no difference whether you take C or D. G gives 0, always, for anything. Now what about F? Now if you apply F, let's first apply F to D. If you apply F to D, well, then you see this pattern does not match D. I mean, this pattern is a tuple pattern. So this pattern only matches tuples, tuples of two components. D is not a tuple of two components, so you have to evaluate D further. So you evaluate D, and then you get this tuple bot, comma, bot. And now, luckily, this tuple x, comma, y matches bot, comma, bot, because you can instantiate x by bot and y by bot. So there's no need to evaluate bot further. X, comma, y matches bot, comma, bot. So this matches then after one evaluation step of D, and so you get 0. So f of D will first evaluate to f of bot, bot, and then f of bot, bot can be, by outermost evaluation, evaluated to 0. Now f of C, again, this does not match C. This only matches tuples. C is not a tuple. C is a variable. So we have to evaluate C. Okay, so we do this, and we get f of C. And we evaluate C again, and we get f of C, and so on. So this does not terminate. So here we have non-termination. So in other words, there is a difference between C and D, because the function f behaves differently on C than on D. For D it terminates, for C it does not terminate. And that means in the semantics of C should be different from the semantics of D. Otherwise, we cannot express the semantics of f afterwards, because f should do something different on C than on D. So what should the semantics be? Well, now here the semantics is pretty clear. The semantics of D should be a tuple. And what's the semantics of bot? The semantics of bot is the bottom element of Z bottom. And here we have again the bottom element of Z bottom. So this is something where we at least know that it is a tuple, but we don't know how the components look like. Now, here we know nothing. Here we don't even know that it is a tuple. So the semantics of this should be something different. It should only be bottom. And now we can see how the domain should look like. The domain should not only contain these elements, but there should be one more element, namely another extra bottom element, which is smaller than all tuples. So for the domains for tuples, we don't just take the cross product, but we take the cross product and then one more bottom element. So we lift this to one more. We add one more element which is smaller than anything else. So this is the bottom element of Z bottom cross Z bottom lifted. And, well, now we can say how the semantics look like. So here the semantics f of D is, so D comes from Z bottom cross Z bottom lifted. So the semantics here is bottom if D is bottom and 0 otherwise. Whereas the semantics of G, I underline this. This is the semantic function. So the semantics of Haskell F is underlined F, and the semantics of Haskell G is underlined G. So here the semantics is always 0 for all D from Z bottom cross Z bottom lifted. So how does this domain look like? If we want to depict it graphically, then, well, Z bottom cross Z bottom, we know how it looks like. This had the smallest element bottom, comma, bottom. And then if we want to get bigger, we have, for example, 0, comma, bottom, or bottom, comma, 0, or 1, comma, bottom, or bottom, comma, 1, and so on. And if we want to be even bigger, then we can get things like 0, 0, 0, 1, and so on. Or here we have this 0, 0 is also smaller than bottom 0, and so on. And now we have one more element which is even smaller than this. So this is the bottom element of Z bottom, and this is the bottom element of this new domain Z bottom cross Z bottom lifted. So this is the domain we take for tuples. We take the domains for all the components, build the cross product, but then we build the lift. We need one more element which is smaller than anything else. So these are domains for tuple types. So now we have domains for base types, we have domains for tuple types. What are the domains for function types? That we already had, so I will simply restate it. So here, step 1, we had domains for base types. Step 2, we had domains for tuple types. Now, step 3, domains for function types. Now that we have already defined, that I will simply recapitulate. If we have something like the type, say, int to bool, then what is the corresponding domain? Well, we take the domain for int, which is z bottom. We take the domain for bool, which is b bottom. And then we take not all the functions from z bottom to b bottom, but only the continuous functions. Or, if we want to have another example, if you want the type of functions from int, bool to integers, then what would be the corresponding domain for this type? Well, you take the type for this. The type for this is z bottom cross b bottom lifted. And then you take all the functions to z bottom, but only those that are continuous. So this is the general rule. Now we know how for any type which uses the predefined base types and builds new types by tupling or by the arrow function constructor, then you can know how to get the new corresponding domain. Now the question is, what happens with user-defined types? So user-defined types. Now this is something we didn't look at yet. So to make life easy, let's start for a user-defined types which are non-recursive. So there is no data constructor where the type that we just defined occurs in the arguments. And moreover, we will start with very simple user-defined types where we have just one single data constructor. So just one data constructor. Just one data constructor. And no recursion. So no recursion, I mean the newly defined type does not also occur in the arguments of the type constructor, of the data constructor. Occur in the arguments of the data constructor. So what I mean is, it's a user-defined type which is defined like this. The user wrote in Haskell a declaration like this, the keyword data and then a type constructor. Now at the moment we are still in the monomorphic case, no polymorphism, so no type variable here. Polymorphism we get in the end. And then just one data constructor. So normally you can have many data constructors and then you write vertical bars between them. In the easy case you have just one. Let's say this is constru. And now constru has many arguments, of arguments type 1 to type n. And with no recursion I mean that these types are different from this newly defined type constructor. So for all types, type I is not the same as this newly defined type constructor. So it's not a recursively defined data structure like nets, natural numbers, or lists. They would use this recursion. We don't want this at the moment. So an example would be some data structure like this. A data structure which I call maybe pair. It has just one data constructor, which I might call comp for combine, and it combines two integers to a pair. So something like this. So this would be a data structure for pairs of integers, and now the objects of this data structure would have the form comp and then maybe 2, 5. Comp 2, 5 would be an object of type pair. Now, pair itself may not be an argument here. That would be recursion. We will look at this later on. And there's just one single data constructor, comp, not a second one. We look at this case later on as well. So, in other words, the type of constru is, well, what is the type? It's a function which first takes an argument of type 1, then an argument of type 2, then an argument of type n, and it returns an object of this newly defined data structure type constru. So, how do we get the domain? We want to have, for every type, we want to have a domain. What should be the domain for this new type constru? Well, it should be something very similar to tuples. I mean, basically, this data type is almost the same as the tuple data type, where you have tuples of type 1, where the first component is of type 1, second one is of type 2, and the last one is of type n. The only difference is that you write a comp in front of it. Apart from this, this is the same as tuples. These, in fact, are tuples of two integers, but you write a comp in front of it. So it's not the same as tuples, but almost the same. So this is almost the same as tuples of type 1, type n. But there is a data structure, a data constructor, constru. But in front of them. They are marked by this data constructor. So what we do is, if the domain for type 1 is D1 and the domain for type n is Dn, is the domain for type 1 and Dn is domain for type n, then what should be the domain for this new type constru? Well, what would be the domain for this tuple type? The domain for this tuple type would be D1 cross Dn, and then the whole stuff would be lifted. Now this would be the domain for this tuple type. Now the domain that we need here is almost the same, but not quite, because we somehow have to make clear that there is this data constructor. So the objects of this domain should be different from tuples, and somehow we have to mark them by this constructor. And so what we do is we do not build an n tuple, but we build an n plus 1 tuple, and the first element is just the name of this constructor. That's all. So we write the name of this constructor in front. So this is used to mark these objects by the name of the data constructor they were built with. So in our example, if we look at this example where we define the data structure pair, then the domain here would be the following set. It would be a set of triples. The first component is always the word comp. The second is something from Z bottom, and the third one is also something from Z bottom, but there's also another bottom element. So, for example, the Haskell expression comp of 2, 5 has the semantics tuple, where the first element is comp, the second is the semantics of 2, which is the number 2, and the third one is, so this is from Z bottom, this is from Z bottom, and here Z is of type int, and this is of type int. Or another example, comp of bot 3, and bot is again an expression of type int. Now the semantics would be the triple, the first element is comp, the second one is bottom of Z bottom, and the last one is the number 3. So we simply build the semantics of all these arguments and then add the name of the constructor in front. And now to make this more readable, to ease readability, we also write instead of writing this as a tuple, we may also write constr applied to D1 to Dn, or even without any parentheses, constr D1 ... Dn, instead of writing this tuple constr comma D1 comma Dn. So in other words, these are just if you write it like this, then these are just the terms that you build from the constructors and bottom. So the domain for are the terms or the ground terms, so the terms without variables, built from this corresponds to the ground terms built from the data constructors and bottom. So if you look at it like this, then all terms that you can build from the data constructors, and here there's just one data constructor, namely constr, and bottom, all those are, this is exactly the domain for this particular type. And in fact, this view of looking at it also works for the base types. So this is also true for base types. So if you look at int, then int, in fact, this predefined type int, in fact, has infinitely many constructors, and they are all of arity 0. So this has infinitely many data constructors, and they are called 0, 1, minus 1, 2, minus 2, and so on. And therefore, the ground terms that you can build from this, I mean, they are of arity 0, so they take no arguments. So the ground terms you can build from them are 0, 1, minus 1, and so on. And you want to take all ground terms built from the data constructors and from bottom, so you get one more because you get this bottom stuff as well. And for pair, well, you get everything you can build. You get all terms that you can build from the data constructors of pair, and there's just one called comp, applied, and bottom, applied to arguments. And for the arguments you have to take, since the arguments are of type int, there you take ground terms built from the constructors of int and bottom. So for pair you get bottom, you get comp, bottom, bottom, you get comp of 0, bottom, you get comp of 0, 1, and so on. So this is the domain, but this is just a nice annotation. The formal definition is these are all tuples. In the formal definition, they are not really terms, but they are tuples where we add this first name of the data constructor as first element. Okay, so this is the definition of the semantics for very simple user-defined functions. And of course we can do it in the same way for types which have just a constructor of arity 0. So for types with data constructor of arity 0, we have the same thing. So if arity is 0, then we would define it like this. We would say a new data type, new type constructor. This is the data constructor, and it has no arguments. So what would be the domain for this new type construct? Now, in Haskell, or well, this domain, how many elements should it have? How many elements of this type can you have? Let's make an example. Let's say we have data, I don't know, data singleton, and the only type constructor is called this. So this Haskell object, this obviously has type singleton. So how many objects does the domain for this data type singleton have? Two. Right, exactly. So this has two elements, bottom and the tuple with the only element this, but this we identify with this itself. So this is the same as the set where we write this, but then we lift it. And indeed, this is what we need because there are an object of type singleton is either undefined or it is the element this. So the domain should have two elements. Indeed, that's completely correct. Okay, and now of course the question is what happens if you have more than one constructor? And I think I will do this on Friday. So on Friday I tell you what to do if you have arbitrary data structures defined by the user. Okay, so see you then.